Finding a second Earth isn't the end of our search for life. It's the beginning of a massive property dispute. One day, probably without much warning, a quiet line in a scientific paper will turn into a headline. A spectrum taken from a nearby star system will show something we've been looking for a very, very long time. Oxygen, water vapor, a hint of ocean scattering blue light back into space. And within a few days, someone will say it plainly. We found another Earth, and it's close. Not halfway across the galaxy, not a distant dream for some far future civilization. Close enough that, for the first time in history, we could realistically start planning how to go there. And that changes everything. For centuries we've asked if we are alone, but the moment we find a second Earth, the question becomes, how many people can we fit on the first ship? And from there, to harder questions still. Who owns a world no one has ever set foot on? Do we preserve it, study it, sell it, or race for it? And if it looks a little too much like home, do we start asking how it got there in the first place? Before we can answer any of that though, we need to be clear about something deceptively simple. What exactly do we mean when we say another Earth? What counts as a second Earth? In astronomy, Earth-like is one of those phrases that sounds precise, but really is not. A planet can be called Earth-like because it's roughly the same size as Earth, or because it has a similar mass. It might orbit in its star's habitable zone, the region where temperatures allow liquid water to exist on the surface. Or it might show signs of an atmosphere that includes oxygen, methane, or other chemicals we associate with life. But none of those, on their own, make it Earth. A Venus-sized planet in the habitable zone might still be a runaway greenhouse world. A Mars-sized one might have lost its atmosphere long ago. Even oxygen, which we tend to think of as a strong biosignature, can sometimes be produced by non-biological processes under the right conditions. So astronomers tend to use a loose ladder of terms. An Earth-like world might just be similar in size or temperature. An Earth analog gets closer, similar orbit, similar conditions, maybe an atmosphere that looks promising. And an Earth twin is the real prize, a planet that matches Earth close enough that, at least at a distance, you'd struggle to tell them apart. But even that last category leaves room for surprises. I would guess most folks are far more familiar with M-class planets from Star Trek, a tidy label for any world where the oxygen is high, the water is wet, and the landscape looks suspiciously like a California hiking trail. For a TV production, Class M is a budget-saving necessity that lets the cast skip the bulky spacesuits, but for a civilization like ours, finding a real one would be the ultimate jackpot. It represents a planet that isn't just Earth-like in size or distance, but Earth-identical, in its capacity to let us walk outside and breathe deep without a helmet. Whatever a true second Earth is, it isn't just about size and sunlight, it's about oceans, continents, climate cycles, a stable atmosphere, and, most importantly, whether it's actually habitable, not just theoretically so. And that's a much higher bar than most headlines suggest. Needless to say, when you hear that we found an Earth-like planet, it usually means we found something that might be a candidate, not a destination. I've seen it casually applied to overhyped headlines describing planets hotter than Venus, or too massive for land life to be plausible. Our window needs to be narrower than that, even if we could plausibly terraform both. Right now, in our exoplanet hunt, almost everything we see is Jupiter-sized, or hotter than Venus, and usually both, because those are vastly easier to detect. Only the last couple of years would an Earth-sized planet in the habitable zone of its system be something we had a decent chance of spotting. Not because we think they are rare, but because they are hard to spot. It's like an elephant and a mouse. It is easy to spot elephant planets, but there are way more mouse planets. Of course, that doesn't mean these are M-class planets in the Star Trek sense. But one day, we may find something that clearly is. Before we get to that, though, there's one idea we should get out of the way, because it's too fun not to mention, too persistent not to address. The hidden twin. For as long as we've known Earth orbits the Sun, people have wondered if there might be another world sharing that orbit, hidden from us on the exact opposite side of the Sun. A true counter-Earth, sometimes called an anti-Earth, always perfectly out of view, always mirroring our position. That's not as improbable as it might sound, either. In orbital mechanics, that point actually exists. called the Lagrange 3-point, or L3, where the gravitational pull of Earth and the Sun balanced in such a way that an object could, in principle, sit directly opposite us in the same orbit. It is a wonderfully elegant idea, and one that science fiction has had a lot of fun with. In early versions of Superman, Krypton was sometimes placed there, hidden behind the Sun, which helped explain how Kal-El could reach Earth as an infant while his civilization developed space travel. The name itself ties in the idea, Kryptos meaning hidden. Other stories around with it too, from Marvel's High Evolutionary setting up a hidden laboratory world there, to Doctor Who's Mondas, the original home of the Cybermen. It is a great concept, and it doesn't work. If Earth and this hypothetical twin were in circular orbits, and if there were no other massive planets in the solar system, you might be able to keep something there for a while. But those are very artificial conditions. In reality, the L3 point is only marginally stable, and the gravitational pull of other planets, especially Jupiter, would quickly nudge anything massive out of place, and eventually into a catastrophic collision or ejection. Needless to say, we would have spotted by now too. We do have telescopes and probes that went beyond Earth's orbit. So if we find another Earth, it won't be hiding behind the Sun. It'll be out there among the stars, and when we do find one that truly qualifies, the question won't be whether it exists, but we what to do about it. The real discovery, a nearby Earth. If we do find a second true Earth, the first question won't just be what it is like, it'll be how far away is it, because distance determines whether this is a curiosity or a turning point in human history. A world 1,000 light years away might still be fascinating, but it's effectively out of reach for a civilization like ours. Even a few hundred light years, a stretch, something for long-term robotic exploration perhaps, not a place we'd expect to settle anytime soon. But inside 100 light years, things start to change. At that distance, we're talking about something that future propulsion systems, fusion drives, beam-powered sails, maybe more exotic concepts, could realistically reach in centuries or less. That's close enough to begin planning, even if not immediately acting. A flyby probe can reach a distant planet far more easily, since it doesn't need to carry any slowdown fuel, which makes the engineering much easier, and I think we'd shoot one out within 20 years of spying such a candidate planet, even if it happened tomorrow. And even if we spotted one tomorrow, we wouldn't see much at first. We wouldn't be seeing continents directly, at least not to begin with. It would come through spectra, tiny fingerprints of light broken down to their component wavelengths. From that, we could tell a surprising amount, though. We'd see the presence of gases like oxygen, carbon dioxide, methane, nitrogen. We might detect water vapor, or even infer oceans from the way the light reflects and polarizes. Over time, we could watch the planet brighten and dim as it rotates, teasing out hints of continents and cloud systems. The Pacific Ocean reflects light differently than Eurasia. Given enough observations, we might even detect seasons, subtle shifts in atmospheric composition or reflectivity as vegetation grows and recedes, or as ice caps expand and shrink. And then at some point, the evidence would cross a threshold, not suggestive, not promising, certain, ironclad, or waterclad with a nice iron core anyway. A world with liquid oceans, an atmosphere rich in oxygen, and perhaps even a telltale spectral edge, a sharp change in reflected light that on Earth comes from chlorophyll. At that point, we wouldn't just be looking at a habitable planet, we'd be looking at a living one. And that's where the real questions begin. It has life. The moment we confirm life on another world, the story splits in three. You've got very alien life, which I would argue makes it not a second Earth. Then alien life that is compatible with us, like the classic space opera planet. And then life that is impossibly like our own, beyond what even a shared panspermia origin might produce. I could do a whole episode on what to do about a planet with incompatible alien life, and I'd say that planet is now less Earth-like than a lifeless one with seas and ocean, which we can get to later, so let's focus on the other two examples for today. Alien life but compatible. In the most straightforward case, the life we find is clearly alien but not completely unfamiliar. It uses carbon chemistry. It depends on liquid water. It thrives in an oxygen-rich atmosphere or something close to it. The details would be different biochemistry, different structures, perhaps even different fundamental building blocks, but the overall system might feel eerily recognizable. Forest analogs, ocean ecosystems, microbial cycles we can at least begin to understand. That kind of world would be the greatest scientific discovery in history. A second genesis. It would tell us that life isn't a fluke, that the universe produces it readily under the right conditions. If we found one within 100 light years of us, it would strongly indicate a few million more existed in this galaxy alone. On the science side, every field, biology, chemistry, medicine, ecology, would be transformed. It would also be dangerous. Not necessarily in the dramatic sense of hostile organisms, but in the quiet, pervasive way ecosystems resist intrusion. Alien virus analogs are probably harmless, but alien microbes probably are not. If they can survive in our environment, they may well thrive after a bit of time and no natural predators, and they might interact with our biology in unpredictable ways. Our own bacteria could devastate their biosphere just as easily. So the question becomes immediate and unavoidable. Do we go there? Do we study it from orbit, send probes, or keep it quarantined as a pristine example of life that evolved entirely separately from our own? Do we settle it, accepting that in doing so, we will inevitably change it, perhaps forever? Because even if the world is compatible with us, it is not ours, and deciding what to do with it may be one of the hardest choices humanity ever faces. Familiar life. Too familiar. But there is another possibility, a stranger and more unsettling one. What if we analyze that distant world, and life there isn't just compatible with ours? What if it's related? Not just broadly similar, but built on the same genetic code, the same DNA structure, the same amino acids, arranged in ways that are unmistakably connected to life on Earth. At that point, coincidence stops being a reasonable explanation. We will be forced to consider two possibilities. The first is panspermia, that life spreads naturally between worlds, carried on meteorites or cometary debris, seeding multiple planets from a common origin. That's a fascinating idea and one we already take seriously in limited contexts, but across interstellar distances, especially in a nearby star system, it becomes much harder to explain. It also wouldn't cover anything beyond the simplest organisms, all long extinct. If you arrive on a planet with functionally identical things, like leaves, that might just be convergent evolution on a good idea. But if you run into oak trees or dinosaurs, you now have a second possibility that becomes more likely. Someone put it there. Not necessarily for us, not necessarily recently, but deliberately. A seeded world, a parallel biosphere, a copy or a variation of Earth life, planted elsewhere. And that opens the door to a very different set of questions. Why seed worlds at all? Why seed them nearby? Why create life that looks so much like ours? You could imagine a civilization spreading life the way we might spread seeds, terraforming planets not with machines but with biology, leaving behind habitable worlds as a kind of legacy, or perhaps something more structured. A cluster of worlds, dozens, maybe hundreds, within a few hundred light years, all pre-prepared, all carrying variations of a familiar biosphere, a kind of cosmic archipelago of garden worlds, waiting for emerging civilizations to discover them. A gift, an experiment, a test, all of the above maybe. Because if we found one such world, the obvious question would follow. How many more are there? And were they meant for us, or if we ever managed to reach them first? We tend to imagine alien life as something waiting around another star, but needless to say, Earth has never been short on monsters of its own. The ocean in particular has always been our closest thing to an alien planet. Dark, pressurized, hard to explore, and full of creatures that seem to have wandered in from mythology after taking a wrong turn at biology. That is the charm of Gods and Monsters from Curious Archive on Nebula. It explores the deep ocean as a place where real creatures and old myths start to blur together. Krakens, glowing life, giant predators, and ecosystems strange enough to make ancient sailors seem less superstitious and more like underfunded field researchers with poor lighting. It's a fun fit for SFIA viewers, and it's one of the reasons I like having Nebula as a place for deeper, stranger science and storytelling. You'll also find my full SFIA catalog there, including monthly exclusives, collections, bonus episodes, and regular episodes early and ad-free. You can use my link with a QR code to get 50% off an annual plan, or 40% off lifetime access, and it directly supports SFIA and the other creators making these shows. If it's barren, but ready. There is, however, a third possibility, and in many ways it may be the most consequential of all. Not a living world, not a dead rock, but something in between. A planet with oceans and continents, a thick nitrogen atmosphere, maybe some oxygen or carbon dioxide already in place, clouds, weather, seasons, but no life. No biosphere, no competing ecology, no alien microbes to worry about, no ethical dilemma about preservation. Just a world that is, for all practical purposes, waiting. That isn't just a discovery, that's an opportunity, because the hardest part of making a planet habitable is building the stage, getting the gravity right, holding onto an atmosphere, maintaining liquid water, stabilizing a climate. If all of that is already there, then what remains isn't terraforming from scratch, it's just finishing the job. And I'd say that raises a very practical question. How hard is that, really? Compared to turning Mars into something Earth-like, a process that might take millennia, this could be dramatically easier. You're not trying to thicken an atmosphere, or warm a frozen world, or build oceans from ice. You're adding life to a system that's already capable of supporting it. That might still take centuries. You need to introduce microbial ecosystems first, carefully building up soil chemistry, oxygen cycles, nitrogen fixation. Then more complex plants, then animals, each stage shaping the next, each step monitored to avoid collapse. Almost a fast-forward evolutionary process. And not too advanced either, because you need to stage slowly to allow adaptation to occur and to let emerging ecosystems settle into something reasonably stable and robust before you dump the next layer on. A shallow, half-developed ecosystem is not a stable one, and it's a bad place to introduce something new that might throw it off balance. You need to seed things in reasonably complementary chunks. If you introduce rabbits, you better include foxes or some other predators at the same time. And even then, you have to be ready for surprises. Maybe foxes turn out to be far more efficient hunters in an environment with 96% of Earth's gravity, or on a planet with 25.3-hour days. Maybe the rabbits breed faster, or slower, or interact with local chemistry in ways you don't anticipate. At that point, you're not just managing an ecosystem. Instead, you're debugging a planet. With more advanced biotechnology, you might accelerate that process, engineering entire ecosystems, seeing them in carefully designed waves, compressing what took Earth billions of years into something measured in decades or centuries. But speed comes with risk, and it's hard to assert deep expertise with a new alien planet when your experience is limited to one single planet. And this episode is on finding a second Earth nearby, not M-Class Planet 923. So, do you go slowly, cautiously, treating it as a long-term project for future generations? Or do you move fast, accepting the risk, because the prize is simply too large to ignore? There is no undo button for moving too fast, except the kind that involves nukes or redirected asteroids. The rush. Who gets a whole world? The moment a world like that is confirmed, the conversation stops being purely scientific and becomes human instead. Because a second Earth, even a barren one, isn't just another place. It's effectively unlimited land. An entire planet's worth of territory, resources, living space, and future history, all concentrated in a single location. And there's only one of them. That creates a kind of pressure we've seen before, but never at this scale. But we do have some rough precedents. Antarctica, where nations agreed, more or less, to set aside territorial claims in favor of scientific cooperation. The Moon, where international treaties attempt to prevent outright ownership, at least on paper. The Age of Exploration, when new continents were claimed, divided, and contested, often long before anyone fully understand what they were claiming, whether someone else already had. But none of those are quite the same. Antarctica is remote and hostile. The Moon is valuable, but not conventionally habitable. Even the New World, for all its scale, was just one more set of continents on an already inhabited planet. A second Earth would be different. It wouldn't just be valuable. It would be uniquely valuable, especially if it had life. Unless it turns out they were all seeded of Earth life in the last million or so years, they would access them galaxy-wide fairly easily, like we see in the Stargate franchise. Each world should have vast amounts of unique life on them, with potential medical and commercial applications. The First Nation, or coalition, or corporation to establish a presence there could set the terms for everything that follows: borders, laws, access, ownership. Those might not be decided by treaties, but by whoever arrives first and can hold their ground. And that creates a core tension that's hard to resolve. On paper, we might argue that such a world belongs to all of humanity. In practice, that sounds nice, but we tend not to play nice for high stakes, so access probably won't be equal. and equal itself is already a concept difficult to pin down in human terms. The ability to reach another star system will be limited, expensive, and controlled by whoever has the necessary technology. So, do we treat it as a shared inheritance? Do we divide it up in advance, negotiating claims before anyone even arrives? Do we try to enforce neutrality, turning it into a scientific preserve or a managed colony? Or do we see a race? Not necessarily a war, but something close. A scramble to be first, to plant the flag, establish a foothold, define the rules. Because for all of our ideals, history suggests that when something this valuable appears, agreement tends to come second. Arrival comes first. And once someone is there, everything else becomes much harder to settle. The economics of a second Earth. Once the initial rush settles, if it ever does, the next question is quieter but no less profound. What is a second Earth actually worth? In space, most resources are abundant and redundant. There's no special unobtainium waiting around on some planet to mine there, and only there unless it's an organic product like the spice melange from Dune. Asteroids hoard vast quantities of metals. Gas giants offer fuel. Entire star systems can be mined, harvested, and industrialized. In purely economic terms, raw materials are not the limiting factor for a spacefaring civilization. Habitable worlds are. A planet where you can walk outside, breathe the air, drink the water, and live without a pressure suit. That's not just another asset. It's something qualitatively different. So, how do you compare it? How many asteroid belts equals one Earth? How many lifeless systems, rich in minerals but empty of air and oceans, would you trade for a single living or livable world? It is not an easy equation because it isn't really about resources, it's about time. You could terraform 10 barren worlds in something comparable given enough time, but one ready-made Earth becomes a major power in a century, while the others are still construction projects. But it is mostly about livability, about gravity wells and ecosystems and the simple, stubborn human preference for open skies and oceans instead of sealed habitats and rotating cylinders. Even in a future where you can build artificial worlds, a natural one, especially one that doesn't need to be built, has a kind of value that's hard to replicate. You could imagine entire interstellar economies reorienting around that fact. Nations might trade access rights instead of territory. Coalitions might form just to secure a stake. Entire regions of space, dozens of star systems, might be exchanged, formally or informally, for influence over a single Earth-like world. Even if you can terraform all those systems, what you can terraform in a century is vastly more valuable than those that would take a millennia of effort, because there will be major powers a century after that, and those other systems will still be weak and vulnerable. And then comes the deeper question: what does it become? Is it held in common, a shared trust for all of humanity, managed carefully, perhaps even restrictively? Does it become a gated paradise, accessible only to those who can afford the journey or a secure place? Or does it serve as a pressure valve, a place to send population, industry, and ambition outward, relieving strain on Earth itself? Each of those paths leads to a very different future, because however we choose to value that world, we will inevitably shape it in the process. How do you divide a planet? Of course, once we decide that a second Earth has value, we run into a very practical problem. How do you divide it? A whole planet is an awkward thing to parcel out. It doesn't come with natural borders or pre-existing claims. There are no established nations, no historical boundaries, just continents, oceans, and decisions of where arise first. One approach would be the familiar one: nations staking out zones, much like territorial claims on Earth. Flags planted, borders drawn, treaties negotiated or ignored. That model is easy to understand, but it brings with it all the same risks we've seen before, only amplified by distance and delay. Other options: corporate, chartered settlements, owned and operated by companies or consortiums, effectively turning pieces of a world into managed assets. Efficient, perhaps, but also raising questions about who actually gets to live there and under what conditions. Then there's the idea of open homesteading. Let anyone who can make the journey claim a piece of land, build a settlement, and expand from there. You set a minimum standard of occupation and usage and how much land can be claimed that way. A frontier model, but scaled up to an entire planet. And it has a certain appeal. It helped turn the United States from rebel colonies to the largest economy on the planet in around 1 century. We also get the potential for chaos, conflict, and very uneven development. It was called the Wild West for a reason. And then there's a more unusual idea: a planetary lottery. If the world truly belongs to all humanity, you'd imagine dividing it not by power or wealth, but by chance, allocating regions randomly, giving individuals, communities, or nations a stake, not because they arrived first, because they were selected. It is an attempt at fairness, but one that would be extraordinarily difficult to enforce. After all, a lottery winner might choose to sell their stake to some person or country that had more money. And doubtless we would see people wanting to swap them so they could be near neighbors of a similar culture as their own. And fundamentally, all these models share a common problem. They assume people will agree. History and common sense suggest otherwise. The risks are easy to see. Conflict escalation as competing claims overlap or expand. Resource hoarding as early arrivals secure the most valuable regions. Cultural fragmentation as isolated settlements evolve independently, shaped by their founders and cut off, at least initially, from broader oversight. And perhaps most importantly, the first settlers don't just claim the world, they define it. The languages they speak, the laws they establish, the norms they enforce, those will set the foundations for everything that follows. Later arrivals may adapt or resist, but they'll always be building on the choices made early on, often by a very small group of people. In that sense, the question isn't just how we divide a second Earth, it's who gets to write its first chapter. Because on a new world, those first chapters tend to last a very, very long time. The long view. A second Earth changes everything. Even finding one such world would tell us something profound, not just about that planet, but about the universe. Because if there is a true Earth-like world nearby, close enough to reach, similar enough to recognize, then it is unlikely to be unique. Planets like ours may not be vanishingly rare exceptions, but part of a broader pattern. And that has consequences. For decades, the Fermi paradox has asked why we don't see evidence of other civilizations, why a universe so vast and so old appears so quiet. One possible answer has always been that Earth-like worlds are extremely rare, that the chain of events leading to life, and then to intelligence, and then to technology, is so unlikely that it almost never happens. But a nearby second Earth weakens that idea. It suggests that early steps, planet formation, stable climates, perhaps even life itself, may be relatively common. That shifts the burden elsewhere, pushing the filters that limit civilizations further along the chain. If Earths are common, then something else is stopping civilizations, and that becomes a lot more concerning. Maybe intelligence is rare, maybe survival is rare, maybe technological civilizations tend not to last, or perhaps they are out there but not easily visible. At the same time, the psychological shift might be even more significant. For all our talk of spacefaring futures, humanity is still, at its core, a planetary species. Every human who has ever lived has lived and died on this pale blue dot. Less than 1,000 people have ever been into orbit, and virtually all of them to low orbit, just a couple hundred miles up. Only a bare handful orbited or walked on the moon. A second Earth changes that. It means we are no longer bound to a single cradle, not in theory but in practice. It turns space from an abstract frontier into a network of destinations. It makes humanity potentially a multi-world civilization. Not someday, but soon enough to matter. One day, that headline may arrive. A quiet observation, buried in data, suddenly recognized for what it is. Another Earth, and close enough to reach. And that world is just a little too perfect, a little too familiar. We have to consider that we didn't find it by accident. And that brings us back to the question we began with. Not just whether we can go there, but what we will do when we arrive. Because finding a second Earth wouldn't just answer whether we are alone. It would force us to decide what kind of neighbors we intend to be.